All right. Hi, my name is Aleksandra Krstic. Thank you for the introduction. I'm very excited to be here to talk to you about Qualcomm Adreno ray tracing capabilities and also give you an overview of a case study we did with tracing primary rays for Mobile NeRF. With that said, I would like to first thank all my Qualcomm technology colleagues for their contributions to this work and all their support along the way. And this is the agenda for my talk. I'll talk about basic Adreno ray tracing features, best practices, and then dive into the Mobile NeRF use case. So let's start with Adreno ray tracing features. So in 2022, we shipped our first mobile chipset that had hardware ray tracing support with Snapdragon 8 Gen 2. And currently, we're shipping Snapdragon 8 Gen 3 series, and it contains our second generation ray tracing hardware. In the past couple years, we've seen good adoption of ray tracing in mobile ecosystem. Many of our internal teams, including Snapdragon Studios, have worked very hard with a bunch of our partners to enable ray tracing on mobile platforms. Some of these are listed here. So just recently, NetEase released Justice Mobile, and then Gaijin worked under mobile as well. Snapdragon Studios is an internal team, and they develop demos to showcase ray tracing capabilities of our chipsets. And I would like to show you the latest demo that they developed called Dragon Alley. It runs Unreal 5 with Lumen on our Snapdragon 8 Gen 3 platform in real time. So it has dynamic global illumination, reflections, and shadows, as well as it's a mix of indoor and outdoor scene. So hopefully the sound will work here. Sorry. Technical difficulties. All right. All right. I don't know why it's doing that to me. All right. Well, if we don't get to it, we'll move on. There we go. So with that said, we support the following Vulkan ray tracing extensions. So we support acceleration structure, ray query, and deferred host operations, as well as their sister SPIR-V and GLSL extensions. Our ray tracing hardware primarily accelerates ray box and ray triangle intersections. And what we found on mobile ecosystem that a lot of people like to use ray query in fragment shader, primarily because it's relatively easy to integrate into the existing game pipeline that they have. All right, so a little bit about best practices. So when you start developing your Vulkan applications for Adreno GPUs, these are some of the things you probably should keep in mind. And I've split these into kind of the build side as well as the traversal side. So Adreno supports both host and device acceleration structure builds. We have a slight preference for building on the host because we can apply additional optimizations and build acceleration structures that are finely tuned for traversal. You can use copy acceleration structure to memory to copy your acceleration structure from the host to the GPU.
My name is
Our GPU builders are capable of building multiple BLASs in parallel. About 30-ish or so we can build at one time. And you can take advantage of this capability through the build acceleration structure command in Vulkan. We also have a big preference, I guess, for fast trace flag at build time. And you should always use that, I guess, if you have static geometry, because again, it allows us to apply optimizations and build most optimal BVHs. And as we all know, traversing is expensive, and the cost depends on the complexity of your scene. So please call your geometry, call everything that is not the unnecessary geometry, because that will allow our builders to build the most optimal BVH and then obviously traverse it faster. So it's a win-win. On the when you're writing your shader programs, be it computer vertex or fragment shaders, some things to keep in mind. Please minimize your call sites to proceed, primarily because, having one or two, it's okay, or having few proceed calls in your programs is okay. Having a lot of them, it's probably going to be detrimental to your performance because it leads to code bloat and prevents our compiler from doing certain optimizations, and as well as it ends up using a lot of registers. Also, minimize number of ray query objects that you create and reuse as much as you can. Ray queries live in GPRs, so the more you create, the more GPRs you're taking off the table for the rest of your shader program. So yeah, create one or two and then reuse as much as you wish. Avoid recursion, enough said about that. And then use ray query data if you need to access it through intrinsics that are available in the language. Please avoid creating your own custom data structures where you're going to copy ray query data into those structures and then use them from there. Because creating your own data structures, again, probably uses additional GPRs that you can't afford to use anyway, and the data is already available to you through the intrinsics. Rays flags are your friend. They exist for a reason. So if you're chasing shadow rays, use your terminate on first hit flag. If your geometry is all opaque or you want to treat it as all opaque, force those flags accordingly. And write your code in a simple way. So help compiler help you. For example, here, if you are chasing opaque geometry, there's no need to write proceed in a while loop. You can just directly call proceed and it will return whatever you wanted to return, closest hit or first hit. And then also consider using ray query in low resolution and then upsampling using our Snapdragon Studios GSR. So there's links to some blogs and source code for that. All right, so let's talk about the case study that we have done, tracing primary visibility for mobile NeRF. So a little bit of a background. So what is novel view synthesis? So this is like a general term for image-based rendering techniques that use 2D images to synthesize novel views of the scene. So some of these techniques have been around for a very long time, some of them since 1990s. But most recently, in the past couple years, right, neural radiance fields and Gaussian splats became really popular to do this. So we focus on NeRF techniques, and more specifically mobile NeRF. So NeRFs really excel in synthesizing novel views from a small number of images using deep neural networks. However, at inference time, so when we have to render these NeRFs, that's very difficult at real times, even on high-end GPUs, primarily because rendering NeRFs is volumetric, similar to volumetric ray marching, where we have to sample hundreds of points potentially along the ray for each pixel. And for each of those points, we have to then invoke an MLP, which is a small neural network. So that can lead to thousands, millions of inferences per frame, which is very expensive. So there is an offshoot, I guess, of NeRF called Mobile NeRF. And Mobile NeRF researchers decided to create triangle meshes and textures at training time as a later representation for radiance fields. Primarily because GPUs have been designed for a very long time to know how to rasterize triangles and textures really well. And it's not a surprise that mobile NeRF rendering beats NeRF rendering by many orders of magnitude. So what is the mobile NeRF rendering algorithm? So this is the original paper published by Chen and al. At 23. This image here presents the pipeline. So they, at rendering time, so at inference, So they take in learned triangle meshes and feature maps as an input. We rasterize those, create these feature images, and then run an MLP for each pixel using this feature image and a camera view to finally render the final output, which is view dependent. So the original implementation was done using WebGL, and it had these two passes. The first pass was premature authorization. The second pass was running the MLP. And one of the things that they use in the original implementation, this is also deferred rendering here, that they use the textures to fetch the weights, so which made it kind of severely memory bound and kind of low ALU utilization. So we thought, like, why not take this algorithm and implement it in Vulkan, kind of more modern API that will allow us to do some optimizations that are closer to the metal. So we last year released a Vulkan sample in Kronos's Vulkan GitHub repository. So that's there today, and there's links in the stock to that code. And this code is very highly optimized for Adreno GPUs. So what did we do to get it optimized, I guess, for Adreno GPUs? So we have two implementations, both released, that support deferred as well as forward rendering. So deferred rendering, we have two Vulkan subpasses, one that takes in a triangle mesh and learn feature map as an input and creates this feature images. And then the second subpass is the MLP subpass. That's where the MLP runs per pixel. In the forward rendering, we have a single pass. Both things run in one large shader. So what we did, we utilized UBOs to load the weights instead of textures. So on Adreno GPUs, UBOs up to a certain size can be stored in constant memory, so that's really fast. We're using Vulkan subpasses. That's another optimization here, as well as in the deferred pass, the output of the rasterization subpass has to be stored in the G buffer, and there's quite a lot of data there that needs to be stored. There's like 12 feature textures that used to be RGBA 32, and we're storing them as RGBA 8. So that's the big downfall of the deferred rendering, is that we have to kind of store all this data out in the first pass to be able to read it in the second pass, and that's not efficient, not super efficient. Could be better. And for the forward rendering pass, we kind of suffer from running MLPs for every pixel because we don't know which pixels are going to end up being occluded. The other thing we noticed about these triangle meshes that were produced during training by neural networks is that they are not really ideal match for traditional rasterizers. They have many unconnected triangles as well as small triangles, right? So we're not getting 100% juice from our rasterizers here. So can we do better? So we are ray tracing people, so we said, well, why not ray trace, right? And that's what we did. So we also have two implementations for ray tracing. We have a two-pass implementation and a single-pass implementation. Pipeline is very similar here. On the build side, so we, all of these Mobile NeRF meshes are static geometry, so we use the fast trace build flag, which again allows us to build very nice trees for traversal. And unlike rasterization, right, with the power of BBHs, we can kind of quickly reject a lot of AABBs and avoid all of these problems with small triangles or bad triangles, and we can quickly cull through the scene, rejecting, not having to look at hundreds or thousands of triangles possibly. One additional thing here that we thought about, but we have not really implemented, maybe a call to action, is that training, when we create these meshes, that's not a real-time process. That takes seconds, minutes, depending on what you're trying to, what kind of scene you're doing. And building BBH is not that slow, but if we could kind of combine creating the mesh and building during the training process, the cost for the building of the BVH is going to be negligible, really, considering minutes to create the triangle meshes. And then potentially, if we build that BVH at training time, then at inference, we just have to kind of load it. But there is no such capability in Vulkan right now to load pre-built acceleration structures. For the traversal, we use fragment shader. We use ray query in the fragment shader. We look for closest hit, and then we also force the opaque flag. The two-pass ray tracing solution obviously still suffers from this kind of large G buffer where we have to store data out, read it in the second pass, but the single pass doesn't, right? So here, single pass comes in for the win, because even though we do have to run MLP for every pixel, here, because of, again, our acceleration structures, we kind of get that depth sorting naturally for most pixels. One thing to note here is that we used mobile NeRF meshes that were kind of trained and created internally. We did not use the original mobile NeRF meshes. And one difference between ours and the original data was the original mobile NeRF models actually contain opacity information, although in a lot of ways that's not necessary. And with opaque triangles, we would have to kind of invoke any hit shaders, and that's not beneficial to your performance on our platform as well as many other platforms. And so now a little bit on the results. So we present here these 4 models, and the number of triangles kind of range from 200 to 400,000 triangles. And on the bottom, I show results from like 2 experiments that we have done. So a little bit of explanation on the graphs. So the y-axis here shows the percentage uplift in performance when you compare ray tracing versus rasterization. So positive numbers here mean that good, meaning ray tracing beats rasterization. And the x-axis, it's just different experiments here. So for each one of these, we compared the single-pass ray tracing with forward rendering and two-pass ray tracing with deferred rendering. And then each bar is one of these models. So on the first graph, we did kind of instancing here, meaning as you go from left to right on this graph, the scene becomes more complex because we started with 1 instance in the scene and then went to 4 and 8, and I think that's kind of where the graph drops off here. So as you kind of can see, as the scene becomes more complex, ray tracing really shines. It starts beating rasterization pretty significantly here. And then on the right side, what I have here is we moved the camera in the scene, right? So we had a camera really close to the object, somewhere in the middle, and then far from the object. And again, most of these cases, ray tracing beats rasterization with some significant percentage amount. All right, so with that, I'd like to conclude my talk. I wanted to show some of the resources, Qualcomm resources here, and there's links throughout the talk as well. So we have Snapdragon Studios maintains GitHub with some Vulkan sample code, including ray tracing, so you can go and look at that. Some of our engineers have given talks at some of the other conferences, so they contain some really good information on optimizations for ray tracing on Adreno GPUs. And then there's also a developer guide where you can find more information. Some mobile NeRF resources. So as I said, we have released our rasterization Vulkan sample. You can find that on Cronus' GitHub. We're hoping to release the ray tracing sample as well soon. So stay tuned for that. And then for Snapdragon Game Super Resolution, some resources for the blog and the code. All right, thank you. And then while we're talking or taking questions, I can also show the NetEase. I don't know where that went. I guess I went into something else. So this is the NetEase Justice Mobile thing. But yeah, I can take that questions while this is playing. Thank you.
Okay, thank you. I don't know there's enough components, but I don't know if it's being,
thank
too
you.
perfect
So
about
maybe,
it.
do we have any questions? So maybe further question. Okay, so I have a question. So maybe you mentioned some mobile NeRF is bit the regular NeRF out of the order.
Yes.
Many of the order. So maybe, so is this because the actual the application terms in terms of the application more like an application where if we have some mobile devices, if there's a kind of the NeRF possible mobile devices, that they will make some more application or some other thing.
Yeah, so with NeRF, right, to render NeRFs, as I mentioned earlier, right, it's really kind of volumetric rendering, which is really slow because we have to do this MLP inferences for at every point along that array for each pixel, and that's very expensive. So mobile NeRF, the whole premise of mobile NeRF was that at training time, right, they decided that their late representation for radiance fields will be triangles and will be textures, and GPUs can do triangles and textures really well, right? So we can avoid that volumetric rendering that we're not maybe quite there yet.
Okay, so my second question is, it seems like only supports some ray query based TXR 1.1. So maybe is that any kind of some region for only for the limited resource in the mobile, or to support the TXR 1.0 shader binding table or some other thing?
Yeah, well, that's a good question. Why we only support ray query? Well, I think that was a strategic decision we made, and we believe that ray query is more kind of optimized for mobile space, and I think what we have found is that a lot of these mobile games want something quick that can be implemented quick in their pipeline, right? So that's why fragment shader, ray query feels like a natural.
Yeah, there is quite flexible in terms of the programming model.
Yeah, programming model easier, right?
But
With
actually,
ray query,
also in terms of the performance, or some of the
performance, right?
There's a pros and cons between two of them.
Right. Well, that's right. So ray pipelines, right, has a lot of. I guess it's a overhead for the implementation more. So I guess the burden shifts, right? With ray pipelines, the implementation is the one that needs to really get things optimized, while with ray query we kind of shift that burden onto the application developer, right, to be able to use ray query efficiently in their fragment in their shader stages. Yeah. Well.
Yeah. Thank you. So. I don't want you to disclose more your company.
Sorry.
Anyway, yeah. So thank you for nice speaking. So maybe nice talking.
You.
So thank you. So I'll let you. Thank you.